In the last section, we looked at matter, which makes up most of the things we interact with. The other thing we interact with that is not matter is energy. The light that you see coming at you and the sound that you hear are examples of energy. We will look at two forms of energy more closely: potential and kinetic energy. So what is energy? By definition, energy is the ability to do work. Fuel stores energy because it is able to do work by powering your car. Moving objects possess kinetic energy. The faster something is, the more kinetic energy it possesses. A car accident at higher speeds will cause more damage than lower speeds because it possesses more kinetic energy. Potential energy is determined either by position or chemical composition. Food contains chemical potential energy in its bonds. When you break those bonds in your cells, you can use the energy to do work by powering your cells. Consider a hydroelectric dam. The water in a dam possesses potential energy due to its altitude. The higher something is, the more potential energy it possesses due to gravity. Once the floodgates are opened, the gravitational potential energy is transformed into kinetic energy as the water moves. When the water hits the turbines, it does work and the kinetic energy is transformed to electrical energy, which we use to power our houses. It's important to note that energy is neither created nor destroyed. It is only transformed from one form to another. This is the law of conservation of energy. Heat is associated with the kinetic energy of molecules and atoms. This is what we measure when we measure temperature with a thermometer. The standard unit of all forms of energy is the joule. Recall by consulting the common prefixes that 1 kilo means 1,000. So 1 kilojoule equals 1,000 joules. In the US system, energy is measured in calories. And 1 calorie is defined as the amount of energy transferred to 1 gram of water to raise its temperature by 1 degree Celsius. 1 calorie equals 4.184 joules exactly. Pause this video and write down 2 conversion factors derived from this equality. When you use these conversion factors in a calculation, do they factor in determining the number of significant figures? Look at the significant figure study aid if you need a refresher. These conversion factors are very useful when calculating the energy content in food. All food we eat contains chemical potential energy, which is energy stored in chemical bonds. When we break those bonds, we obtain that energy. Most of the energy that the body uses is from carbohydrates. These include sugars and starches that we eat. If we use up all of our stored carbohydrates, we can also break down fats and then proteins to obtain energy. This is one reason that if you want to burn fat, having a low calorie or carbohydrate diet can be beneficial. The energy content in food is displayed on food labels. You can see the calorie contributions from fats, carbohydrates, and proteins. The energy content in carbohydrates, proteins, and fats is shown in this table. Note how fats produce twice as much energy as carbohydrates. No wonder burning fat is not an easy thing. One way to determine the chemical potential energy in food is by using a device called a calorimeter. Using electricity, you can ignite a food source. All the energy from the food is transferred to the water as heat. This heat causes the molecules in water to move faster and cause the temperature to rise. By knowing the temperature change and a physical property called the specific heat, you can calculate the heat transferred from the food. Pause and recall what a physical property is. Specific heat is the amount of heat that is transferred to raise 1 gram of a substance by exactly 1 degree Celsius. We can use specific heat to calculate heat transferred as well as to identify different substances, since different substances have different specific heat values. To calculate specific heat, divide the heat transferred by mass times temperature change. For water, the specific heat is 1.00 calories per gram degree Celsius. Some examples of specific heat values are shown here. Note how metals have very low specific heats. This means that they only require a small amount of heat for their temperature to change. This is why we use metals commonly as cookware, since they readily transfer heat. On the other hand, note how the specific heat of water is very high compared to other substances. Water requires a large amount of heat before its temperature rises, which is why water is the most common coolant. When heat is added or removed from a substance, a change of state can occur. We know that when we heat ice, it melts, and when we keep heating the liquid, it boils. We will learn how to describe the changes of state at a molecular level and calculate the energy changes associated with it. A phase change occurs when one state is transformed to another at constant temperature. Now, is this a physical or chemical change? Explain why. During a phase change, heat can either be added or removed. The amount of heat that must be added to convert exactly 1 gram of a solid to a liquid at the melting point is called heat of fusion. Since melting and freezing are reversible processes, the same amount of heat must be removed from 1 gram of a liquid at the freezing point. This heat does not contribute to an increase in temperature, but to breaking the intermolecular forces as the solid melts. For water, the heat of fusion is 80 calories per gram. Heat of vaporization is the amount of heat that must be added to 1 gram of a liquid to form a gas during boiling. For water, the heat of vaporization is 540 calories per gram. For practice, convert 80 calories and 540 calories to joules. Also, write the conversion factors for heat of fusion and heat of vaporization. Vaporization is the phase transition from a liquid to a gas. The two examples of vaporization are evaporation and boiling. Evaporation is when molecules of a liquid that are at the surface of the liquid gain enough heat to overcome the attractive forces in the liquid and form a gas. This can happen even below the boiling point. For example, if you leave a drop of water on a table, it will evaporate even though it didn't reach 100 degrees Celsius. Boiling occurs at the boiling point, when all the molecules in a liquid have enough energy to escape the intermolecular attractions. So evaporation occurs at the surface, while boiling occurs throughout the liquid. And evaporation occurs even below the boiling point, while vaporization occurs at the boiling point. We can represent the change in temperature as heat is introduced into matter using a heating curve. Starting with the solid at the bottom left corner, heating the solid increases the kinetic energy of the molecules and temperature increases. This is represented by a diagonal line. At 0 degrees Celsius, ice molecules have enough energy to overcome the intermolecular forces in a solid, so melting occurs. All the heat added during melting, which is the heat of fusion, overcomes intermolecular forces, so there is no increase in temperature, which is why the line is horizontal. Heating the liquid increases energy of the molecules, so the temperature increases. Molecules at the surface can escape through evaporation. At 100 degrees Celsius, the heat supplied, which is the heat of vaporization, overcomes the attractive forces in a liquid as it forms a gas. Continued heating increases the speed and kinetic energy of water vapor. The cooling curve is the reverse process. Horizontal lines represent phase changes at constant temperature, while diagonal lines represent a change in temperature. So the two phase changes are condensation and freezing that are represented by the two horizontal lines. We have come to the end of the chapter. The concept map shows you everything we have covered. If you need further explanation on any concept, please feel free to email me. We will do problems in class to help you master the material. And as always, happy studying.